What I'd like you to consider drawing into the diagram are all the forces that act on the beam. But instead of drawing it as a free body diagram as you've been trained, I would like you to draw the forces on top of this diagram. There's a reason why we need to do it this way. If you wish to draw a free body diagram, by all means, draw one off to the side. That will help you understand why this problem can't be solved with forces alone. So take a moment, and then I'm going to ask for a couple of volunteers to talk to me about what forces they drew in. So here we go. Rudy, give me one of the forces, please.
Tension.
How would I draw that?
You can do it from left to right with the rope.
Okay. So something like that. So I'll draw it similarly on my little dot there. Fantastic. Drew, give me another one.
Normal force from the wall,
How would I draw that?
directly to the left.
Okay. It might be harder to see up there, but I'll draw it over here too. Fantastic. Let's see. Kevin, give me another one.
Weight, so gravity, so directly down.
All right, so in order to draw that, it's easy to draw here. Where would I draw it on the bar?
In the middle.
Yeah, unless otherwise specified, we're going to assume that our objects have uniform mass, and if they are of a uniform shape, then their center of mass will be what we call the center of gravity. I want to talk to you about that term, center of gravity, because it plays a role in our discussion this week. And if you've never heard the word before, center of gravity and center of mass are not the same thing. By definition, they are different. So to appreciate the difference, the center of mass is something we've already calculated. We know it's the weighted average of where the mass of the object appears to be. And that's not the right way to say it, but it's like an average. It's a location within an object, so that at that location, we have an even distribution of mass around that point. The center of gravity is different. The center of gravity is a point within the object to which all of the gravitational forces acting on the object can be said to act. That's a little more complicated, because the truth is, gravity acts along every piece of mass of the bar. Because of that, we would have to break this bar up into a lot of little pieces and talk about the individual forces acting on each piece of the bar and where it acts relative to, say, the pivot point. Now, if we break it up into all the same size pieces, would you all agree that each one of those would have the same size gravitational force? If I take this uniform bar and break it up into 10 pieces, each piece would have the same mass, therefore the same weight. So the size of the gravitational force would be the same. In that circumstance, we can say that the center of gravity is in the same location as the center of mass. The book proves this, but let me just tell you that the only time the center of gravity won't be at the center of mass is if gravity affects one part of an object differently than another part of the object. The only time the center of gravity won't be at the center of mass is if the force of gravity acts differently on one part of the object than the other. Oh, hi, Jackson. How you doing this morning? We know. That's okay. I was worried you were going to hit your head, though. You were making the play for it. Besides, my voice is like a lullaby. We all know that. Those melodic tones, that nasally sound, it just can put anybody to sleep. Especially given that all I'm talking about is physics. That makes it worse. Let's face it, it's not going to get any better than this. So, the center of gravity and center of mass, it's really the same thing. The book makes a huge deal about it, but the one thing that we're going to be adding to this is, in a few minutes, we're never going to be using free body diagrams the same way. So, and this is important because it could come up on the exam that you have to draw a free body diagram for the bar, and a free body diagram can't tell you what it will take to solve the problem about the bar. But they still might ask you to draw a free body diagram, which still requires that you take the mass of the bar, issue it as a point, and then draw all of the forces acting on that point, of which we're missing one right now. What's the one we're missing? No, I'm not going to use friction here. I don't think the bar is going to slide down the wall. You could use friction, and that wouldn't be a problem. But even if we assume the bar is fastened to the wall here, there would still be an upward force on the bar from the wall. No matter what you label that as. If you wish to label it as friction, fine. But if you were actually to build this, do you really think you would put the bar against the wall and hope it won't slide down? Some idiot's going to jump up there and knock it down. So you'd probably fasten it to the wall. Either way, the wall is very likely pulling up on it. Very likely. I don't think it's friction. There will be a case in a minute where friction would be the answer, but I don't think this one. Now, the thing about center of gravity that I do want to point out, something that it's not always about what's on the test. Let me say it that way. If we're in the Earth and we're looking around at objects here, everything in the room, and I would argue that probably everything in your everyday existence is all experiencing the same acceleration due to gravity. So gravity is affecting all things the same. And this is because we're all about the same distance away from the center of the Earth. Only if there's an appreciable difference in the gravitational force will there be a difference in the center of gravity. So on the Earth, we don't see any shift between the center of gravity and center of mass, but there are cases where it's different. And a good example of that is the moon. The moon has a difference between the center of gravity of the moon and the center of mass of the moon. The moon is relatively uniform, so its center of mass is at its center. But one part of the moon is experiencing more force of gravity from the Earth than another part of the moon. The side facing the Earth is experiencing more gravity than a side facing away. Now, this is not a big deal on the moon, but it is what has locked the moon's rotation in such a way that the same side of the moon faces the Earth all the time. That action on the moon means we never see the dark side of the moon. And whether you've noticed that or not, that means that the moon rotates at the same speed that it revolves around the Earth. Perfectly. We all always see the same side of the moon, as did all of our ancestors. Even pictures of the moon drawn thousands of years ago still show the Sea of Tranquility in the middle of the moon, in the same way that we see it when we go out at night. Now, on the other hand, there are other places where that has been a huge problem. The rings of Saturn and the rings of Jupiter were created because moons got close enough to those planets where the force from the inside of the moon was much greater than the force on the outside of the moon, and it pulled the moon apart. So almost all the rings around any planet had been or were moons that got close enough to those planets to be ripped apart by those, what they call tidal forces. But it really is just the fact that the force on the inside was different than the force on the outside. By the way, we've never talked about it, but that should also indicate why the rings don't revolve around the planet at the same rate. The inside rings revolve faster than the outside of the rings. So rings around Saturn, Jupiter, Uranus, Neptune, they're very complicated. In fact, there's a couple of things about them that we do not understand. We know that inner rings do fall into the planets from time to time. They lose enough energy and just fall in. We are not exactly sure what has created the gaps in the rings, why there are specific holes. There are places where there's just a gap, and we don't fully appreciate or understand why. So they're kind of interesting. Maybe you, as a scientist, will someday discover that. I have at least one or two astronomers in here, but today we don't know why. All right. Let's just put the theta right there for us. Now, that theta and that theta would have to be the same, wouldn't they? I gave you the mass of the bar. What I would like all of you to do is kind of prove to me why we can't figure out the tension with what's written right now if all we had to go with was net force equals 0. And what I mean by that is I'm going to challenge you to write two force equations, one in the x direction and one in the y direction. And I'm going to pick on two people. You can understand where I'm going with this, right? Because somebody in the room is going to tell me what the net force in the x direction equals, and somebody else is going to tell me what the net force in the y direction equals, and I really hope they get it right. So you have 3 minutes. All right, Colin, net force in the x direction.
Got t cosine theta minus n.
Equals?
0.
Yep. Anybody want to offer a fix to that, or are we good? Yeah, I think so. I think it's good. Excellent. Excellent. All right, Vaughn, net force in the y direction.
T sine plus F minus mg.
T sine what?
Plus the force plus F minus mg equals 0.
All right. Any question about that? I think we're good. Two equations, how many unknowns? It's 3. We know theta because we have geometry to help us figure out theta, right? This is something that you guys often miss, so let's be very aware. Theta is known because I gave you enough geometric information. Do you guys see that? Now, I'm not trying to sneak it in there, but that's what I would expect of you to be able to do at this point. Use the inverse tangent to figure out what that angle is. But at the same time, normal force is unknown, the force from the wall is unknown, and the tension is unknown. So 3 unknowns and only 2 equations. There is no direct method to figure out our answer. Even if this force was friction, which would be related to the normal force, because the normal force isn't known, it really doesn't help us very much. So we're at a loss for how to deal with this problem unless we have more information. Problems like this require that we look at net torque at the same time as we look at net force. Not that net torque will solve the problem, but net torque will give us more information. It'll provide a third relationship. So I want to talk about how net torque can be used to solve this problem, or at least contribute to this problem. This is a whole discussion in itself about how we use net torque, and it's not going to necessarily be straightforward, but what I need you to understand is you will reach problems like this and not necessarily know whether to use net torque or not. But consider this problem has a clear indicator that torque could be used. If the string were to break, do you realize that the pole would likely rotate about this axis? Does that seem possible? If you have a problem where there is the possibility of rotation, then torque might suit you to solve a problem. However, what I'm supposed to say to you is that all statics questions require an analysis of torque and force. All statics questions require an analysis of torque and force. It's just that I've only presented problems that can be solved with force to this point in the year. But the truth is, we should always have been looking at torque. Now, to do what we have to do here to talk about torque, I'm going to open up a new page here. I'm not going to rewrite these, but you will need access to this and the picture. I'm going to simplify our diagrams to give you some things you might want to do when it comes to solving the torque portion of a problem. Here, it looks like to me, if I knew what the tension was, I could figure out the normal force and the force from the wall. Right? In one shot, I could get the other two. It seems to me like trying to pick a pivot point that would let me solve for the tension gives me more information. On the other hand, here suggests you can figure out the other forces. And I don't want to spend a lot of time on that. I think you can do that. Substitution and doing math is your forte. You guys are good at it. But yeah, you can go right here and figure out how hard the wall is pushing. Which, again, if the wall is made out of stucco, you might have a problem. Or if the wall is made out of wood, you have a problem. You may not have enough force to be able to maintain the beam against the wall. Ask that question again.
Okay, like for the first one, you determine.
All right. Let's advance it because we're going to run out of time. Yes, ma'am.
Okay. When you're determining the angle, you compare the direction of the force to what other thing? I'm confused.
It really isn't much of an advance, and we will run out of time, and I will expect you to try it for homework. This is the bridge problem. And when I say bridge problem, these are common questions that are often asked in physics. So the bridge question usually has something like this, where there are two supporting pylons, and they might be located, say, 20 meters in on both sides. And the bridge, say, is, I don't know, 120 meters long. So the ground comes up to either side, but the ground does not support the bridge. Okay? You guys see the idea of this bridge problem? You would never build a bridge this way. This is just contrived for the state of this question. Now, here's what I want you to consider. A truck drives across the bridge. Now, as the truck drives across the bridge, it could be anywhere on the bridge. Does it make sense that the pylons are going to provide normal forces that are going to change as the truck drives across the bridge? Let's put the truck here. And say that it is 2,000 kilograms located 10 meters from the inner pylon. And let's say that the bridge is of uniform density and is 2,000 kilograms as well. What is the normal force from each support? They are not the same. Please, please try this tonight. It should take you less than 10 minutes. So you should start by indicating the four forces that just act on the object and where they act. There's at least two upwards forces. Normal force 1, normal force 2. They're acting 20 meters from the outside edge of the bridge. There are two downwards forces. Help me out. The bridge was how much?
2,000.
So 20,000 newtons. And the truck was the same?
Yes.
The truck is at one end. Doesn't matter which end you pick. We're going to get the same answer. So you should start with a net force equation. 1 or 2 dimensional, depending on the problem. This one is 1 dimensional. I didn't see this on more than half the people's papers, but I'm going to assume if I didn't see it, it's because you remembered it or remembered you had it from the prior problem. This part has not changed. And what I'm about to say, I think, is kind of important. You write it down. The sum of the 2 normal forces has to equal 40,000. How that's distributed is all the way based on where the truck is. Which means as the truck traverses the bridge, the normal forces are being redistributed all the time. Now, they have to sum to be 40,000, but they can be any combination of that. In fact, it's possible for one of these normal forces under bad conditions to become 0. That means that support's not, supporting it at all. That's right at the precipice where the bridge begins to tip the other direction. You've stepped on something and popped it forward before, even if it's just a skateboard, so you understand what I'm talking about. You could put enough force down here to cause the bridge to lift, to actually pivot. We're assuming it stays static. In fact, should you work this problem out and find that one of the normal forces is in the opposite direction than you thought, that means the only way the thing stays stable is if these pylons pull down on the bridge. An unlikely circumstance. So when designing the bridge, you're hoping that doesn't happen. Now the torque part is exactly the same as before. We're going to choose a pivot, anywhere's fine. And then we have to start making decisions about the 3 torques that are left. And several of you started to do this, but several didn't. Look, you can do whatever process you want when you're proficient, but when you are struggling and you're not able to do this, do it my way. I should have seen them listed vertically. That's the only way I've trained you. So whatever the hell you guys were doing that was like having them, don't. Do it my way. That's all you get for right now until you're proficient. And there are the truck, there's the pylon or the normal force, whatever you want to put there, and then there's the bridge. You need where they are, how much force they apply, and I don't really think this is a big deal. They're all 90 degrees. Look, the next one we're going to do is not like this, so let's finish this one up quick so we can get to a hard one. Now, the truck's 20,000. The bridge is 20,000. The normal force is unknown. Where they are relative to the pylon. So the normal force is still 80 away. The truck is 20 away. And the bridge is 40 away. Now, positive or negative here is from the right-hand rule. Or, I want you to listen to this. I like using the right-hand rule. I like talking about whether this torque is causing it to twist one way or twist another. Some of you are confused by this. Just put that on the floor. You don't need it. Some of you are confused by this. So let me give you an alternative. And I want everybody to look at me for just a minute so I know you're actually paying attention, because some of you are confused. An alternative is to draw a coordinate system here and just put positive, positive, negative, negative. Any R that's to the left, make negative. Any R that's to the right, make positive. Any force that's up, make positive. Any force that's down, make negative. You could do that and it would work. Your book does it this way. I don't like that method because it has limitations. The moment this is no longer horizontal, it becomes harder. And then our very next one won't be horizontal. But some of you are having trouble with the concept of the right-hand rule. So this will work. Again, I don't like this. But if you at least think of it from here, you're likely to get some recognition that you have to consider positive or negative. I like just thinking whether it's going to make it turn one way or turn the other. That's what I like. But you might not follow it that way. The way I have this drawn, do you want this way to be positive or this way to be negative? All right, so this way is positive. That would be a torque that is into the board or into the page. So when I start looking at torques, the truck, where it is going to cause a positive torque. It's going to cause the system to twist that direction. It's applying its torque on the other side of the pivot point. Or you could right-hand rule it. R is going to be that way. The force is downwards. My thumb is into the board. Again, positive. When I look at the bridge, R to the bridge is that way. The torque is downwards. Thumb is out, so I have to make that one negative. R all the way to the pylon, still that direction, but the force is upwards. So I'm into the board here. That means that one has to be made positive. So once I know that, come down here, make my truck positive, the pylon positive, but the bridge negative. They sum to be 0. Now this will produce the answer for N1, where N1 comes out to be 5,000 newtons. They have to sum to be 40,000. That means N2 has got to be 35,000 newtons. Now, you don't have to do it that way. You're more than welcome to put the pivot over here and do another equation for torque. But I think that's a little overkill. All right. Is the ladder question. I really like students to see it because it's pretty challenging, but also it is one of those problems that's done a lot in the literature. So when we look at physics books and textbooks and classic examples, this is one of them. It's not likely to be on the exam because it's in every single textbook, but I'm pretty confident you guys don't read the textbook, so this is a good one for us to do. So the ladder question is exactly what it sounds like. We're going to have a ladder that's leaned against a roof or leaned against a wall. I got to see if I can do this the way I'd like to. Oh yeah, here we go. So I'm going to spare you some of the difficulty of this problem by saying that the wall has no friction, okay? But the ground does. The ground has a coefficient of friction of mu s, the static coefficient. For the time being, to make it easy, nobody's standing on the ladder. And it is leaning against the wall at an angle theta. What I want you to do is twofold. First, I want you to find and consider all of the forces acting on the ladder and draw them in this diagram the way it's indicated right now. And then we're going to strip that away and try and create a torque diagram from this. So please take a moment and draw in all of the forces acting in the system. I'll wait very patiently. Give me one of the forces.
Friction going to the right.
All right, so friction drawn as an arrow to the right. Where should I draw that on the ladder itself?
The bottom of it.
All right, so friction. Yep, good one. Earth triangle.
I put normal force like at the bottom of the ladder, like this.
There's a normal force at the bottom of the ladder upwards. I would agree with that statement. Hogsmeade X.
MG at the middle of the letter down.
MG at the middle of the ladder. If we're not told anything, we have to assume that's at the middle. Winterfell D-pad.
Normal force on force from the wall on top of the ladder.
All right, there's a normal force from the wall at the top of the ladder. Put wall and ground. All right. Now, at this moment, if you have not done so, you need to figure out all the angles. Okay? I'm going to allow you to do this really in a simple fashion. You can use theta for anything that is the same as the angle the ladder makes with the ground, and phi will be any complement to theta. So, for right now, put in theta and phi where they go on the diagram. Phi is a circle with a line through it. Theta is not a circle with a line through it. Theta has, like, Charlie Brown hair on top. It stays connected. All right, I'm going to just call people out. There's only 3 angles you have to put down. So, Paradise Falls. There's no D-pad at Paradise Falls. Yes, there is. D-pad. Give me one of the angles.
A number?
No, just tell me. Like, I'm looking at, pick one of the forces and tell me where to draw the angle for it.
The one that's already there? I don't know.
There are 3 forces. There are 3 forces where I do not know what the angle is. I want you to tell me whether it's theta or phi. Which force?
NG.
All right, so NG, this angle here, and what angle do you think it is?
Me?
Yep.
Phi.
Thank you. This isn't hard. Asgard triangle. Tell me a force and what angle to put with it.
Phi for MG.
Here?
Yeah.
Okay. Paradise Falls. Sorry, guys. Circle. I don't know.
The theta for NW.
Yep. All of it true. Now, if you had difficulty with that, get over yourself. That's what you have to be able to do. Figure out where all of those different forces are and what the angles are. Now, this part I think is going to be harder than I anticipated based on what I just saw, but you should start this problem as a net force problem. So please take a moment and come up with what your net force equations would look like. Not done anything new yet. This is all old stuff. And I'll be honest, there's only 2 of them. Net force in the X, net force in the Y. All right, that's enough time for this. There's not a whole lot to do here. So, halo array circle. Who's there? Go ahead, give me one.
For the net force in the x direction is the force of friction minus the normal force of the wall.
Yeah. Thank you. And Winterfell X. Kevin.
Normal force from the ground minus energy.
Yep. All right, so let's contemplate the way this question would be asked. What would be a likely piece of given information? Yes, sir. Mass of the ladder. Yeah, I think that'd be a likely piece of given information. Now, if we look at this problem, normal forces tend to not be given in problems like this. They tend to be reactive to what's happening in a situation. At the same time, there's a variety of ways this question can be asked. For example, one of the more likely questions is to try and figure out what theta is for a specific mu. So if you place your ladder on a somewhat slippery surface, what angle do you have to place it against the wall so it won't slide back? A more common and easier question is to give the angle and then ask what must mu be for the ladder to stay in place. I know you guys like having numbers in your questions. It makes it easier for you. So I'm going to do this. This will be the last one we have numbers in for a while. But we're going to say theta is 60 degrees. And the ladder's mass is 30 kilograms. And the ladder is 2 meters long. Now, before we even start, the only actual unknown is mu, because that's what I'm asking you to find. But right now, what things do you know and what things don't you know in your force equations? Take a moment and just underline the things that you would not be able to figure out with what you have. Okay, this one's harder because there is a deceptive thing happening here. So I will let people raise their hands, and I just want one thing at a time. Somebody raise your hand and tell me at least one thing that you would know. Yes?
The weight.
Sure, I will know the weight. Somebody raise your hand, tell me then something you know. Yes, Zach?
Normal force from the ground.
Sure, if I know the weight, I know the normal force from the ground. Anything else that I know? Yes?
Would you know the normal force from the wall if you knew the normal force from the ground?
No. As we see it here, the normal force from the wall is only related to the frictional force. One of the rookie mistakes, or a mistake you might make, is we can't use this. Because that's not true. It's not an equal sign, is it? So this frictional force can't be derived from here because this is an inequality. We don't know how much friction there is. We don't know if we're at the limit yet or not. So that can't be guaranteed. And since we don't know the force from the wall, we're going to have to use torque to solve this question. So, I don't know that we need to redraw this, but where is a good place to put your pivot? Yes, ma'am. Bottom of the ladder. Now, I'm not going to redraw this one, but if that's the pivot point, please create a torque equation. And I think you need to list out your torques and so on and so forth. We're almost out of time. Let's try and get this problem laid out so you can complete it tonight. Because the bell's going to ring in a minute. How many torques are there? Two. Do you want clockwise, for lack of a better term, right now, or into the board? Do you want them to be positive or negative for the torque? All right, so into the board for the torque or clockwise is positive. So the ladder's weight causes a torque. What is the R value for the ladder's weight? 1. And then we're going to have the weight of the ladder. What's that?
300.
And what should I use for the angle? 30. That's right. If you're paying attention, that's what you would have. Do I make this torque positive or negative? What's that? Positive. That's right. You could right-hand rule it. Or you can just realize that the weight's going to make the ladder come down. All right. We have another torque from the normal force. What do I make the length of the torque arm?
2.
We don't know the size of this force. But what's the angle? These have to add up to be 0. Now, the bell's going to ring in just a minute, so please hear these next few words. They're important. Doing this, you will solve for the normal force from the wall, which is friction. And here you already have the normal force from the ground. This gives you the minimum coefficient of friction necessary for the ladder to stay there. If the coefficient is actually 0.9, how high can a 60 kilogram person climb the ladder? If the actual coefficient is 0.9, how high can a person, 60 kilograms, climb the ladder? That's the ladder problem. It's not the ladder by itself. It's with the person on it. Torque problems can't be solved using a free body diagram alone. Torque problems really need more extension. So generally, when I go to solve a torque problem, I try to remove as much information as possible, but leave the appropriate extension. To us, that's pretty easy because a bar is kind of one-dimensional. So I'm drawing just the bar. There will be cases where the bar alone isn't enough. But for right now, I'm trying to make the problems relatively straightforward, so the bar is enough. And we should, before we even go any further than this, indicate all the forces acting on that object as part of our diagram. So the same 4 forces, but I'm placing them where they act. And the reason, I think, is fairly understandable. Torque is all about the torque arm, where the force acts on the object. It makes a big difference for how much torque there is. So our objects have to have extension. Moreover, these are not unknowns. We know that this distance from here to here is 1 meter. We said it's at its middle and it's 2 meters long. And this distance from here to here is 2 meters. Now, that's kind of messy. I'm going to take it out of the picture, but you should have it in your notes. Now, the thing about torque problems is that unlike force problems, in the past, we always reduced all the forces, all our objects to a single dot. Now we can't do that. So what we have to do instead, and this is paramount to understanding, is torque has a point of reference. It has the point of rotation, the axis. That is a point of reference, and we must assume that to be able to calculate torque, we will need to know what that axis is. Now, some problems have a natural axis of rotation. It's mounted to the wall here. So this is a natural axis of rotation. Now, what I'm about to say is the most important, most critical sentence for statics problems. So I'm prefacing it as this might be more important to get written down and something to reference in the future. Since the system is not moving, or since the net torque is 0, any point can be chosen as your axis point, your pivot. This is counterintuitive. It goes against what you think. This problem, like I said, has a natural pivot. But it doesn't matter. Since the net torques are 0, our object is not going to accelerate, so its inertia doesn't contribute. Because of that, any point can be chosen as the pivot. Now, the reason that's important is because a torque is the product of R times F times the sine of the angle. That's our definition of torque. But for a problem where there is a net torque of 0, us choosing the pivot means we can create conditions where R is 0 by carefully choosing a pivot point. In fact, that is what we will do. We will always try to choose a pivot point that eliminates a force. Like I said, this one is a natural problem. This one's easy. The pivot point was already chosen for us. And better yet, by keeping the pivot point there, it eliminates 2 forces that we don't know. So I would definitely leave it there. But in any statics problem, you can pick your pivot. You can put it anywhere you want. And any place where you choose to put it will work in solving the problem. You should always try to eliminate a force. That doesn't mean eliminate an unknown. It just means to eliminate a force. Because if we look back, if I place the pivot point, say, here, which I could do, and it would work, I would be able to get answers. By placing it here, I create the condition where I will have a torque equation that has 3 other torques, all of which are unknowns. It will create an equation so that I now have 3 equations and 3 unknowns. That's harder. So we attempt to put the pivot in a useful location. And in this case, the natural place of the pivot works out for us. Our next example, not so much. I'm going to purposely choose an example where the pivot is ambiguous. And we'll have to figure out where to place the pivot. All right, let's move forward here. I tend to do these problems a little bit more drawn out. You don't have to, but I do. With a reminder that it's R dot F dot the sine of the angle. I have to hurry. Jordan's checking her phone, so she's in a hurry. So I will point out that there are the potential for there to be 4 torques. There's the torque from the tension, the torque from the weight, the torque from the normal force, and the torque from the wall. 4 torques, which have to sum to be 0. I'm going to list them just like this. Since every torque requires 3 pieces of information, setting it up like this, I hope, will help you. Also, torques are positive and they're negative. So I have to choose what positive means. I'm going to assume that a torque that is into the board is positive. Right-hand rule means that a torque that is that way is considered a positive torque. Yes, ma'am. That okay? Better? So, here we go. Let's start with the first torque, the one from tension. I have several things I need to make sure I look for. Torque arm length, size of the force, and the angle. Well, R is 2 meters. That's pretty easy. F is unknown, it's tension. I don't know what the angle is. It's whatever the result is of the inverse tangent of 1/2.
26.6.
Okay. So the angle is actually 26.6. Thank you, Cameron. 26.6. Now, one thing you will find out is that for smaller angles like this, sine and tangent are so close to each other. There's really not that much of a difference, but you should always work it out. Is this torque positive or negative? Now, technically, I think it's easy to tell that the tension is causing the beam to go clockwise, which should make it positive. But technically, I should do the whole, okay, R is in that direction. The force is generally right that way, which means that my thumb points into the board, so that's also positive. Technically, that's what I should do. You okay? All right, so either way, this torque is positive. Let's go to the weight. Weight's not so bad. Write it all out there. First, the weight acts 1 meter away from the pivot. The weight is 600 newtons. Right, 60 kilograms, 600 newtons. And it is the sine of 90 degrees. On the other hand, this force is trying to make the bar go counterclockwise. Right? It's pulling it down. It's going to cause it to rotate counterclockwise. And just use my little rotating rule if I really want to say it's going to have a torque out of the board. But, of course, we know the right way to do it. Torque arm, my middle finger points down, thumb points out of the board. That still indicates a torque that has to be negative. Takes some getting used to. All right, the normal force. Look, the sine is 180 degrees or 0 degrees. So automatically it doesn't cause a torque. But also the torque arm length is 0. So it really won't matter. There is no torque from that normal force. It does not cause the bar to rotate. The one from the wall, well, it's 90 degrees for sure. But it also acts at the pivot point, so it's 0. Now, we've listed out all of our torques. They sum to be 0. So it's going to be 2t sine 26.6 minus 600 sine 90 equals 0. Any question about where any of that came from? The sum of the torques has to equal 0. Statics problem. So you now can figure out T. Now, I don't think there's a whole lot left here. I mean, you can do the mathematical work and get a number, which I do believe you should, just as practice. 300 divided by the sine of 26, I don't know, it's going to be a little more than 600.
670.
What's that?
I got 670.
Okay, 670 newtons. I hope you notice that that's more than the weight of the beam. Do you notice that? As potential, engineers, putting the cable like this means that you need cable that can support much greater than the weight of the beam, which might surprise you, but it has to do with the angle. The angle plays a big role here. The smaller that angle is, do you realize the smaller that angle is, the more tension there's going to have to be? That you might reach a point where that angle just doesn't work out. I mean, if you just look here, it ended up being 600 divided by 2 sine theta. As theta gets smaller, sine of theta gets smaller, t gets bigger. It's possible for that to go to infinity. I mean, if that angle starts to approach 0, you can't find a cable strong enough to hold the beam. So these are design constraints, considerations on how you would operate that. The 2 has to do with the length. So obviously the longer the beam, the better. But again, if you're trying to design something, there are design constraints. You have to work within them. Now, we have the tension.
Or it was like the second one, it's a sine of 90, you took the 90-degree angle, I guess, because the weight's down, but what are you comparing? That's just like the way the board is?
Yes.
Okay,
Yeah,
gotcha.
I was assuming that the beam was horizontal.
Okay. Gotcha. Okay.
Don't assume that that's what I'm going to do on a test. In fact, your homework has situations where the beam and stuff like that is not horizontal. So you don't get accustomed to that. I just thought I would start with a easy one. Folks, when it comes to statics questions, this was the easy one. The next one I'm going to give you is one step harder.